discuss with us new irrigation scheduling methods for cotton.
Okay, good morning, everybody. My name is Kelly Thorp, and I'm a research scientist with the USDA laboratory that's to the north of you at the university here, UArizona here. And my primary role as a research scientist, I don't really have an extension appointment in the things that I do, but I do very much applied research, and I hope that some of the things that I present today about our findings could be useful to you. So the USDA began a program in overhead sprinkler irrigation starting in 2014. This hasn't been a very common practice at U of A, and there have been a few instances of small lateral moves or pivots being used on the farm, but nothing that was used very consistently or for very long. But in 2014, the USDA established a field site just north of here where we installed a 6-span lateral move system. It's a ditch-fed system. It pulls water from an existing canal here on the farm. It's diesel-powered. And the field is 16 acres. The machine is 1,200 foot long and it travels 600 feet. The USDA has made this field site kind of a mainstay in our research in irrigation over the past decade, almost. A year later, we added the commercial technology. So most of the overhead irrigation companies have their technology that's variable rate irrigation, or it's the system that can be installed on their overhead sprinklers that allow the rates to be varied spatially over the length of the machine. And we have found this to be a very important piece of technology for conducting our research. I think the companies like to market it as something else. It's more like a site-specific irrigation technology or being able to do variable rate irrigation in our field. And it has potential there, but for me as a researcher, the main thing about this technology has been being able to set up field experiments and apply different rates of water spatially across the field according to different treatments that I'm imposing using this variable rate system. So it basically works. There's a main panel here, and I can upload a map of the field that I create on the computer where I specify, where rates should be changed across the field. I can upload that map here. Then as the machine moves across the field, there's 2 GPS receivers on each end of the machine that locate it, and then it calculates the different rates that should be applied at each location at its drop hose. And each drop hose is fitted with a valve. Okay, it's a wireless communication. So as the main computer calculates the rates, it's communicating wirelessly with these they call nodes inside the box. There are 88 nodes across the length of the machine, and each node controls 4 valves, a group of 4 valves. And so that's basically how the machine works to control differential applications of water between 0 and 100%. Basically, if the valve is closed 80% of the time and open 20% of the time, and that's how it does a 20% rate. If the valves are open 100% of the time, then that establishes your 100% rate over the field. The field is located here. We're sitting here in this building. The USDA facility is to the north. So if you're interested in seeing it, you can travel up this way on your way out today, although I'll warn you, you'll probably run into some kind of detours and road closures. You might not be able to find your way back out of there. I think this road's closed now, and you have to back out this way to go out today. So dating back to 2014, we have done a set of 4 different experiments using this particular field and this particular machine, at least related to irrigation management. I do have collaborators in the field that also work on cotton breeding, phenotyping technology for cotton and other things. Today, I'm going to focus on irrigation studies that we've done. There have also been some research done in nitrogen management for cotton, but that was done by a previous scientist who's now retired. So in 2014 and 15, we were kind of getting our feet wet with overhead sprinkler irrigation. Obviously, this is not a technology that has been used very widely on the farm, and most of us were familiar with furrow irrigation for cotton at that point in time, and we had to learn how to use this new technology. In those years, we basically focused on comparing different irrigation scheduling algorithms or computer-based calculations of how to apply and make an irrigation decision. In 2016, 17, and 18, this is when the first year we had our variable rate irrigation system, and I was trying to learn how to use that thing. Basically, in those years, I set up an agronomic study, a rate study that looked at different irrigation amounts and timings applied to cotton, with focus on, what were the fiber yield and quality outcomes from administering these different rates. In 2019 and 2020, I tried to really increase the technology. I really wanted to test the modern technologies that are being proposed for irrigation management in this field. So I'll talk more about that. In particular, I was using drone technology to image the fields on a weekly basis. And I wanted to actually use this VRI system to apply irrigation on a spatial basis to see if I could make improvements in yield or water use efficiency. And in last year and the current year, we are moving back to testing irrigation scheduling software for making irrigation decisions, while also incorporating measurements from soil moisture sensors into these algorithms, with again the goal to look at if these technologies can be used to improve yield or improve the efficiency with which we use water. So 2022 is our 9th year of studying irrigation in cotton in field 13, bench 4, and I'm going to take you through some of the highlights of our experiments that we've done. 2016 through 2018 was our cotton irrigation rate and time experiment. The maps showed the field layout in 16, 17, and 18. There were 64 plots with 16 different irrigation treatments that were replicated 4 times across the field. And again, the differential amounts were administered to each plot based on our variable rate irrigation system on this lateral loop. The rates were 60, 80, and 100 and 120% of a recommended amount that came from our irrigation scheduling tool. So we basically run the tool, and then based on whatever rate it was recommending for that week, we'd adjust the rates down to 60, down to 80, and up to 120% to test the effects of those adjustments. There were also 2 timings of the season that we focused on. The first timing was from square to peak bloom, and the second timing was from peak bloom to full. So the goal of the experiment was to test the different combinations. If you do the different combinations of the 4 rates and the 2 timings, you come up with 16 treatments. So it could be one plot, one treatment received like 60% in the first period, and then 100% in the second period. It could be that another plot received 120% in the early period, and then 80% in the second period. So we're testing all these different combinations, totaling 16 treatments. So I'm going to take you through the results for some of the agronomic measurements that we measured as part of this rate study. I'll focus on the left side, but the right part of the figure is more kind of for the research side of things. The left side gives you the actual measured data that we collected, where on the X would be the rate that we used in the first period, and on the Y would be the first. Comes to that. On the Y-axis would be the rate rate that was used in the second period of the season. So you can see for fiber yield, essentially the 100% rate, this represents the recommendation from our irrigation scheduling tool. So this would be like following the guideline that our irrigation scheduling tool required, and then all the other squares represent decisions to go up or down from that recommendation. So the first conclusion is that our scheduling tool is doing fairly well. If we reduce irrigation by 20% in the second half of the season, we get a yield hit on that. If we increase by 20% over the whole season, we're not really improving our yield by much by making that choice. The only thing that can be said is that by reducing irrigation by 20% in the first period, the yield doesn't change that much. So that's sort of the conclusion, is that's where our opportunity is to try to fine-tune adjustments in how we're managing our water in the first part of the season there without having a yield impact. This is a look at the seasonal evapotranspiration or water use. This value is calculated based on our soil water sensors that we had installed in each plot. And basically it follows the irrigation applied. Okay, so if you apply less water, essentially you get less water use. If you apply more water, the crop's going to use it. That exactly follows the applied irrigation in this case. This is a look at water productivity, or otherwise known as water use efficiency. Essentially the kilograms per meter cubed, sorry, metric. I think it's most important is the relationship between plots, but the unit is metric. So what it is a weight of fiber produced per volume of water, kilograms of fiber per volume of water used to grow that crop. Again, the results are showing that the opportunity to improve our efficiency lies in our decisions that we make in the early season by moving from the recommended rate down to the 80% rate in early season, bump in water productivity. It also shows that there is opportunity for reducing waste by clarifying how we terminate irrigation. We look at all the rates that were 20% higher in the latter part of the season. That's where we get our lowest efficiency. So probably what's happening is we're over applying at that point, and there's a point in time where the plants are not using that water to create any more fiber production. It's sort of wasted some water by leaving too much in the soil after the plant is finished. And so there's opportunity there to clarify how we decide to terminate the irrigation for the season as a way to improve our efficiency of water. This is a look at the result for Micronaire. Probably know the premium price for the Micronaire is between 3.7 and 4.2. In this particular study for this variety, we could not really achieve Micronaire within that range. All of our Micronaire was high, above 4.2. So it was hard to get Micronaire within the premium range for this variety over these 3 years in this study. So I guess the conclusion then is it may not be wise to try to use extra water to try to get there with Micronaire. This is a look at the fiber strength. Essentially, it shows that if you're here at 100 rate, you drop down to the down by 20% or by 40% of your water in the second period, you get a hit in fiber strength. The pattern of this figure looks the same for a metric of fiber elongation when the fiber fails. So the basic take-home messages for this rate study that we conducted was that the opportunity to improve our efficiency with water management is in the early season. And so I've worked to, over the years that I've spent in this field, I've worked to reduce and even eliminate the pre-plant irrigation. I don't apply any water before planting at this point in time. Basically, the water that I'm applying to emerge the crop is enough to fill the profile down to a meter and a half, and that's adequate. You don't need to do any pre-plant irrigation. Also, technologies and strategies for optimizing our early season, our early vegetative growth irrigation decisions seems to be a way that we can improve our efficiency over the season. Finally, full irrigation is required during bulb filling. We don't want to under-irrigate in the second half of the season. This is what's required in order to maintain our yield and to maintain our high quality. The only opportunity for improving efficiency with water management at the end of the season is by clarifying when we shut it off. Clarifying when we decide to terminate the irrigation can have an impact on our efficiency. So those are the basic take-home messages for those that 3-year study.
Overwater burning, does that mean that plant less efficient later?
Yes, because I consider the water use as like a full season measurement. What do you use? When I calculate this water efficiency or water productivity, I'm looking at all of the water that was applied from April to September. That's like basically I'm thinking of that as the total amount of water that I used to produce this end result of fiber. So if you over apply early in the season and the crop is not actually using that water to any benefit, then it's wasted. It becomes a wasted amount of water that's not helping us produce. Okay. Yeah, I've heard that. You know, it's kind of I've heard that argument too. You want to put on lots of water in the early season and have it be there. I guess the point I would make is that I think in my management, I think I'm applying enough water during emergence to fill my profile to full. Basically, I'm applying maybe millimeters. So it's probably like maybe 4 to 6 inches of water that I'm applying, basically from planting till a month after planting, just to get the crop emerged and get it established. Okay, and this is actually more water than the crop is using. So some of that water is being stored in the soil and basically doing the job of filling the profile in the first month. And I think that's enough. I think that's enough. I think that's what's planned. So in 2019 and 2020, my thinking shifted, and I began to really try to question and test these new technologies that are being proposed for irrigation management. And a variety of those technologies included like looking at soil variability maps and making decisions spatially across the field, looking at drones, looking at imaging of your field and how can that be used, and also looking at this technology called variable rate irrigation or site-specific irrigation, which is the idea of differentially applying water in spatially, based on some technology which tells you that something is different over here than over here, and I'm going to adjust my irrigation accordingly. There were 4 treatments in this 2 years, and the complexity of the technology that was used to make the decision increased over the 4. The control treatment was just a simple irrigation scheduling tool. It was an FAO56-based irrigation water balance evapotranspiration calculation tool. It uses a curve like this to help calculate how much water is being transpired or used by the plant over the seed. It didn't use any data, any measurements. It just ran the tool based on the azimuth weather data here on the station. And irrigation was applied uniformly over all of the treatment areas for this treatment. The next thing I did was add a spatial soil map. So we went out in the field and we measured the texture at various locations across the field. It came up with a map of soil variability across the field. Those soil data were then input to the model to try to calculate different rates according to different soil texture. The third thing I did was add a drone technology. So here's a drone that was flown over the field once a week to image the progression of the growth of the plants. And then that drone data was used to replace this curve. So instead of using this default curve, we used the cover amount of vegetation as measured by the drone to replace that. Then finally, this is like basically the treatment that tried to put all the different technologies together, including a spatial soil map, an imaging technology on a weekly basis, and then using that data to come up with a spatially variable recommendation for how to change the rates across space. This is a look at the field layouts. Plot map in 2019. Here's the 4 treatments that I just mentioned, and this is how they were distributed across the field. And here's the 3 randomized in 2020. The bottom 2 are a look at the map of soil texture variability. So this represents the field capacity or the drained upper limit. And this one represents the wilting point or the lower limit across the field. It's kind of a gradient across the field this way, low to high. This is kind of a sandy spot in the field, and this is more of a sweet spot where you get some good production usually. So there's 4 treatments, 6 replications. This was done over 7 acres. You notice that each of the plots is subdivided into 24 little squares. Each of those squares is 6 meters by 6 meters. And that was the resolution at which I did all of the spatial aspect of the study, including mapping the soils, including doing any kind of analysis of the drone data, and including applying a irrigation amount site-specifically. For the treatments that required site-specific irrigation, it was done at the scale of the little 6-meter blocks in each plot. This is a look at the drone flights that were done. So we flew the Phantom 4 Pro over the field, and we collected RGB images. Those images were stitched overnight to create a single image for the field. And then a set of processing was done to calculate and end up at this map shows essentially the fraction of pixels within the image within each of those 6-meter zones that were plant versus soil. So if it's more green, it means there was more plant material in that particular location. If it's less green, it means there was less plant material in that location. Theoretically, the darker green ones would require more water than the others. Kind of trying to measure study. A quick look at the results. Basically, the treatments that were managed by drone reduced the water applied about 100 millimeters, 4 inches in both years of the study. So 2019 results and 2020 results. We have irrigation applied, we have yields, we have water productivity again. So treatments that use the high technology ended up pulling the irrigation recommendation down. For the treatment that was managed by the drone alone, but without spatially variable irrigation, that resulted in a 5% drop in yield in 2019 and a 26% drop in yield in 2020. Remember, 2020 was a very hot year late in the season. So we had, in a dry year, so we had quite a hit that year from the lower irrigation applied to this treatment. The main success of this study on high-tech irrigation management was found in 2019 with the variable rate irrigation treatment. Essentially, in that treatment, I was able, using all of this technology, mapping the soil, flying the drones, getting the images, and having the technology available to differentially apply water spatially across the field. I was able to reduce the irrigation applied by 8%. The yields were not different across between this treatment and control treatments. And that led to an increase in water productivity by 6%. So anyway, one success out of this study. But overall, my take-home messages are that, you know, drones and remote sensing data, that it's kind of always been touted as like the up-and-coming thing. I still think it's the up-and-coming thing. It's promising, but these technologies are complex and they require careful utilization in order to figure out how to get it to work. So it needs more work to make it practical for on-farm decision making. A comment about spatially variable irrigation or variable rate irrigation. Again, any company that manufactures overhead sprinkler systems is going to have a technology that they call their BRI technology. And they're going to try to market it to you and sell it to you. It's promising, obviously, but it's also very expensive technology. Also, it first requires a shift to overhead sprinkler irrigation in order to make use of it. My personal opinion, after doing a study kind of like this, is that I think we still have a lot to be gained from improving our irrigation scheduling via uniform irrigation before we talk about trying to spatially apply our irrigation rates. That's my opinion. Based on the results from that kind of high-tech experiment that I did in 2019 and 2020, in the current year and in the previous year, I've tried to come back down and try to focus on technologies that might have more practical value. In 2021 and in the current year, I am testing 3 different irrigation scheduling tools, including our FAO 56-based approach that we've been working on USDA for a number of years. Also, AquaCrop is a irrigation scheduling tool that's developed and maintained by the Food and Agricultural Organization, the FAO-based irrigation management tool. And then the DSAT cropping system model is more of a research level tool. It's a very complex model of water balance, nutrient balance, and crop growth, which we use for a lot of different research applications. So those are the 3 irrigation scheduling tools that I'm using. In combination with that, I'm also incorporating feedback from soil moisture sensors. For our research studies, we use neutron probes. It's like the tried and true accurate method for measuring soil moisture. And so that's the technology that I'm using for measuring the content of soil water. 2 varieties were tested. So this is another new aspect of this year is that I've added 2 varieties that we use. Makes for some interesting comparison. Using next gen 3195 and next gen 4936. Thank you, Karen. This is a look at last year's results of this study. Remember last year we had a lot of rain in midsummer, late summer. We had 8.5 inches of rain here on the MAC, and it's like more rain than I've ever dealt with in my time here at MAC. So it's kind of a unique year. And the results for irrigation showed me something very interesting and useful about using soil moisture sensors in our irrigation management. These 3 treatments here are basically the recommended irrigation schedules from the scheduling tools, from the models, without any feedback. You just sort of look at the tool and it does its calculations based on the weather data. And, you apply that amount, and there's no feedback based on what's going on in the field. The other 3 are when I've used data from the soil moisture measurements to feed back on those models and adjust them. Because we had so much rain last year, all of the treatments that were based on feedback from soil moisture sensors reduced our required irrigation by about 100 millimeters, maybe 4 inches or so. And if we take a look at yield, statistically, there was no difference in yield among any of these treatments. So the basic take-home message for this first year of this experiment was that I think that soil moisture sensing really appears to be a pretty straightforward and promising practical technology for assisting with our irrigation management. So in 2022 now, we've got this same experiment going in the field as we speak, and we'll see what the new year brings. I'd like to kind of summarize my experience working with cotton irrigation management over the last 8 or 9 years or so in this field. Basically, these plots show annual data from 2014 to 2021, where on the left here, this is cotton fiber yield in pounds per acre. The blue represents the now county average cotton fiber yield in pounds per acre. And the red represents what I've been able to achieve in my fully irrigated treatments during my field studies using these, variety of technologies to try to assist in irrigation management. Now on the right side, it's the same years. It basically shows the amount of water that I applied in irrigation, and then the red shows the additional rainfall that we received in that year. The basic idea for me is that I'm able to kind of meet or exceed the now county average yield in most seasons, and I'm doing that with 3.5 feet of water per year for my treatments that are fully irrigated, so it's full production. So I just provide that just kind of as a reference for you. You all know where you are in terms of how your yields come out and the water that you're applying. That's kind of where I am. So final thoughts. I think there are becoming more and more options for soil moisture sensors commercially on the market. A lot of them have kind of cellular uplinks, so put the sensor out in the field and then there keeps a time series of soil moisture uplinks that to the internet through the cellular link, and you can kind of install it, see how it tracks over time. I think this is kind of a positive, simple and practical technology, particularly based on some of my results where I've seen the importance of feedback on soil moisture data. I've also talked to a few growers, one grower out of Wilcox that manages a vineyard, and he was sold on this kind of technology for helping his water management in his vineyard, commercial soil. Something else that I'm working on are irrigation scheduling phone apps. There's one group of apps called the Smart Irrigation apps, and these apps come out of the University of Florida and Georgia. There is one that's being developed for cotton, and it's rooted in the FAO 56 scheduling technology that we also incorporate in some of our studies here. I am participating with this group. They have recently added ASMET as an option within their cotton irrigation scheduling app. And they are working with me in some of my field experiments. I've sent them data. They're trying to essentially validate this tool as an irrigation scheduling app for cotton in Arizona. I think at this point, it does require more testing and feedback. So if some of you have interest in apps for irrigation management, might be one to check out and maybe provide feedback. I'd also like to mention that the University of Arizona is currently in the process of hiring an irrigation extension specialist. This is a position that's been vacated for quite a long time. When I came here to Arizona in 2007, it wasn't too long after that this position was vacated by the previous person. And this position has been vacant for a decade or more now. So I'm happy to say that UA is in the process now of interviewing and selecting candidates to fill this position. So we will have a irrigation extension specialist located at MAC to be able to come and provide these kind of talks these days about updates on irrigation management. And as I said at the beginning of my talk, I'm primarily a research scientist in the things that I'm doing. So I'm very excited to have this position be filled, and I anticipate that I'll be working closely with this person to interconnect our research programs with its extension program. And so thanks for your attention, and take any questions if you have.
Thank you, Gary. I think we'll